All right. So today we have to go a little bit slow because half of the class is missing, taking another exam. But the good news is we're moving away from linear algebra, not because we have covered more than 50% of what I would have liked to cover, but somehow because we really need to do something about differential equations because that's supposed to be a significant part of the course. In many ways, the course is overloaded. You have linear algebra, you have differential equations, but you know what? It's the only required course. And in some sense, abandoning you without telling you something about differential equations would be embarrassing because that's all. Some of you will never take any other course, period. You wouldn't even know what an integral is 6 months from now. All right, so what we're going to do is we're going to cover ordinary differential equations. Most of the topics, to me, they are undergraduate level, right? There's nothing fancy, but what I'm going to do is I'm going to try to cover systems of ordinary differential equations and bring ideas from eigenvalue problems and singular value decomposition, all of these things, to discuss interesting aspects that have to do with the stability of the solutions of ODEs and dynamical systems in general. And we're mostly interested in qualitative aspects. So in this part of the course, you may have to do almost in every homework some programming to get the solutions to the problems of interest, okay? And don't ask me how you do this or that. I want you to go and find out, all right? So if you go to MATLAB and you say ODE toolbox, you will immediately come up with 20 videos that give you guidance on how to use ODEs in MATLAB. The same thing with Mathematica. If I search on the web, I will find tutorials on everything. Okay, it's there. But I will not cover those in the class because if I do, we're not going to do anything. Okay, we're starting. No panic. Okay, so we're talking about first order ODEs, and the course is going to be, the lecture for sure is going to be extremely elementary today. As a reference, for significant part of the course, I'm going to use this very standard book by Boyce and Di Prima on elementary differential equations and boundary value problems, okay? So for me, this is going to be the textbook, not because it contains unique information, simply because I will follow it, and it has a lot of qualitative information that other books don't have, okay? Now, in principle, mathematics is so generic subject. If you want to find references for the topics I'm covering, you can find a million books that contain the same information. All right, so that's why I'm not saying buy this book or buy that book, because they're all the same. And they all have as one objective to make money, okay? So make money with ordinary differential equations. That's a big deal, you know. One day somebody asked me to write a calculus book for China, actually. He told me we're going to make so much money. All right, and I see a big audience just arriving. So we were just waiting for you, blah, blah, okay? And why are you going to the back of the room? You should know. Okay, so, and the second reference book I'm going to use is this book on advanced engineering mathematics that actually contains much more information than ODEs. So if you're going to take the second math course on PDEs, this is a very good book to have as a reference. There is another book written by a former Cornellian with the same title. It says Advanced Engineering Mathematics by Greenberg, that I would have recommended, but I was told that there is a new edition of the book coming up shortly. So in essence, if you go and buy it, the value may go down 50% in 1 week if the new edition comes out. But the textbook by Greenberg is also very nice. Okay, so let's talk a little bit about mathematical fields. I'm going to be zooming through the slides rapidly. If you have any questions, you ask me, okay? So obviously, we're going to discuss about models that are described with differential equations, okay? And I I don't have to tell you much about it. All of engineering, all of sciences is models with differential equations. So in principle, one course cannot do justice to all these problems, and I give you, if you are interested in fluid mechanics, you better know lots about partial differential equations. If you're interested in robotics, you have to know lots about dynamical systems and ODEs. If you're in electrical engineering, the same thing. If you're doing heat transfer, if you're doing civil engineering, seismic, earthquake modeling, if you are in biology, you just mention it, right? PDS is the subject, okay? And really, if you want to learn the subject, you have to take a course in the math department that covers these things in some serious depth, because our course is not going to cover anything to a serious depth. Computational things. I mean, our course is a baby elementary course, right? So we don't cover, but in your homework, I'm going to ask you to do a lot of computational assignments, but I will not teach you anything about them. So basically, you'll be solving ODEs, for example, using Mathematica or MATLAB, because I don't want you to do lots of calculations by hand. I'm more interested in the qualitative aspects of the solutions. So I'm going to tell you a little bit on how you get things that are in MATLAB, but I'm not going to tell you anything algorithmic. This is not the right course for that. Not that we have a right course, by the way, or any course in that subject area. That's another discussion. Okay? All right. So let me just give you one trivial example, right? So I'm going to put all of these things up. And again, I have no time to read everything, but if you look at the free fall of a mass m under its own weight with some air resistance that is proportional to the velocity v, you can write a differential equation effectively like that. All right, so this is the force on the mass equal to the I'm losing my voice equal to the weight of the mass minus this resistance force gamma v. So effectively, this equation comes from balance of forces. That's what it is, right? So what leads to differential equations as models for physical problems are some balance equations. And this is what I have here, all right? So you have seen this, says the force is equal and I write the force m times the acceleration equal the weight minus this resistance that I am assuming that is proportional to the velocity v. So if you plug in some numbers, this is an ordinary differential equation. And I will actually solve this equation in the slides in a few seconds. T there is the time. And in essence, if you provide some initial velocity to this problem, this is what is called an initial value problem. Right, an initial value problem. So lots of problems in ordinary differential equations, this variable may be spatial variable like x, for example. Here for initial value problems is time, okay? So when you see t, really it implies time. Since I want to teach you about qualitative things, right? So here is this equation, and somebody tells you, can you tell me something about the solution of this equation without solving it? Because really, you should be able to dream on how things look like, not expect to put it in the computer and say, oh, the computer gives me this solution. So if somebody tells you, how does this thing look like, you need to have some sense of that, okay? And the sense comes by plotting, and I ask you to do this in the homework problem, of what is called the direction field corresponding to this ordinary differential equation. Can you guess what's the direction field? Maybe you already have done this in your other undergraduate courses. What's a direction field? You can see from the table that is given here on the left, right? We're going to look on the right-hand side of this ordinary differential equation, okay? And we're going to compute the velocity, the acceleration v prime, all right? V is my unknown here, so dv over dt. We're going to compute v prime for different velocities v. And this is why I call this a direction field. So let me just plot it. I want you to look at it, and try to guess what these little errors potentially show. So I plug in various velocities v's there, right? And this is what I had on my previous table there. So I put v to be 0, 5, 10, etc. I computed v prime, which means really I computed the right-hand side here. And then I plotted this, all right, with the correct, with the correct orientations, okay? So I plotted dv over dt. So what is this and why is this helpful? If you have, so does everybody have a sense of what these errors mean? It tells you that at each location, all right, it tells you if v prime is positive or negative and in which direction. Okay? So why is this helpful qualitatively to understand the solution of this equation? Can you tell me at first what is v prime on this straight line that I see there on the middle? What is v prime on that straight line? And can you tell me what's the value of, so v prime is 0. So what's the velocity v for this straight line? I mean, I can read there. It's most probably, what is it? 45 or something, 47, something like that, right? Can you look at the equation and tell me where this number that leads to this straight line comes from? Where do I get this value for this straight line? Look there. How much is v prime when you look at this straight line? 0. So what is this value of v that it's plotted for this straight line? What is the physical meaning of that straight line? Say it again. There is no acceleration. So give me a name for that straight line. It tells you something about what type of solution. The equilibrium solution. Okay? It tells you something about the equilibrium solution. So in what you see on this plot, right, we don't solve the differential equation. We can imagine to solve this ordinary differential equation, we need some initial conditions. We need to say, if I start at 0 velocity at 0 time, what the solution will look like. And actually, if you have this plot of the direction field, if you start from this location, you know how the solution will look like. You will follow the arrows, and you will go asymptotically to the equilibrium solution. That's what the purpose of the arrows are, right? It tells you, if you start from one location, how you're going to be moving, and here you're going to be moving, reaching the equilibrium state. Okay? And similarly, if you start from somewhere there, from any location at time 0, where are you going to go eventually? You will also go asymptotically to the equilibrium location. Okay? Now, obviously, this is a very simple problem, right? And you can look at the equilibrium location is 9.8 divided by 0.2. But generally, and I ask you to do this in the homework, you will see that these direction fields may be much more complicated, and the nature of the solutions you get for different initial conditions may be very complicated. So you may have various stable and unstable modes that you will need to recognize in the solutions. And to be sure that you do it right, just be sure that when you plot these direction fields, the axis, the range that you use for the time and the velocity, for example, they are large enough to basically show you what's going on. Because here, for example, if you go and plot this from 0 to 20, you will never see the equilibrium solution. Okay? So be sure again that you scale this properly. All right. So we talked about all of this, so keep going. And again, you will find, as you do the homework, more about this type of things. So let me take a differential equation that looks very trivial. A little bit to simplify my notation, when you see y prime there, it means dy over dt. And mainly, I'm interested on initial value problems. So my independent variable to start with is time. All right, so the equilibrium solution for this will be when y prime equal to 0. So the equilibrium solution is b over a. This is what we had before. So let me, this is a very standard example with ordinary differential equations, and every textbook actually has this example. So this example has to do with the population of mice and owls. And so let's call the population of mice in your hometown as P. All right, so this tells you how the population changes monthly. All right, and it tells you that the mice reproduce with a rate of 0.5, all right, per mice. That's a high productivity, right? That's why you don't want to have one in your house. All right, so if P is the population of the mice, the growth rate will be 0.5 times P. But if you have owls around, okay, they eat 15 mice per day. Wow, that's big. Is that what it says? Per day, which means 450 per month. So dp over dt is the growth rate minus the reduction because they're being eaten, right? So that's a nice problem in population dynamics where you have two species competing with each other. And as simple as this problem sounds, we're actually going to extend this to system of ordinary differential equations later in the course, and you will see this population problem represents a paradigm for many, many, many problems in physics and engineering, okay? So for right now, you can see there is a growth rate, but there is, in this particular case, there is also a reduction because the owls are eating the mice. Okay, so here is the direction field, all right? So the direction field looks like that. Not very much different from what we did before. So the equilibrium state will be P equal to 900, all right? So this is what you see here. And you can you look actually and tell me what happens? Let's say if my initial population of the mice at time 0 is 880. What is going to happen to the population of the mice? Looking at this picture. So if you start with 880 mice in your city, or in your town, or in your building, okay, what is going to happen if you start with that and you trust that this direction field is correct, okay? You can actually put different pieces and you will see what you get. This is what you get. So if you start with 880, what does this diagram tell you? It will decrease. Okay, it will decrease. Actually, you can see it. All right, there is an exponential decrease here. We will see it. But if you start above 900, unfortunately, you're doomed. Okay, you're doomed because the population will increase, and there is nothing you can do about it. And actually, you can guess, right, where people are using these models in population dynamics because they take counts of how many deer they have in a town and you know, how many of this and that, you know, and then they figure out where the population is going to be 10, 20 years or 100 years from now, and if there's going to be an extinction or not. This is the type of problems they're solving. Okay. All right, so let's talk a little bit about the classification of differential equations. Can you tell me what's a differential or an ordinary differential equation and a partial differential equation? One independent variable, right? And in our case, for example, up to now has been time. It can be location x. Partial differential equation is when you have more than one independent variables. So you can think something that is a function of the location x and y, and let's say time. So that's a partial differential equation. By the way, really I would like at the end of the semester to at least give you 2 lectures on PDEs, because if you don't take the second required course, it's like never heard PDEs, it's like not going to look good, okay? And so, but there is so much material to cover, I don't know if we will reach that point, but this is what I want to do, okay? So these are some ODEs, Okay, and again, the independent variable is time. And I prefer to call this initial value problems, because if you think initial value problem, immediately your head goes to time, and you know you start from some value of this, of the velocity or of the population of the mice, and then you try to predict how this changes with time. All right, so it's an initial value problem. So here are some partial differential equations, and again, if we have time, I want to discuss the solutions to both of these equations. So one of them is, both of them involve space and time, but the space involves only one variable, the way they are written here. So you can see the wave equation having an acceleration term, and then the heat equation. The solutions of the two equations that you see here are very different from each other. Okay? And here is a system of ordinary differential equations. So still I have only one independent variable that I call time, but you notice the dependent variables here are two, u and v. And the evolution of u depends on both u and v, and the evolution of v depends both on v and u, okay? And actually, this model here, this predator-prey model, it's an extremely important model to understand if you want to understand dynamical systems, right? So for anybody who works in robotics, etc., this is a standard model that you need to understand. And you can, because you have a system here of two equations, actually we may be able to use some linear algebra to solve this system of equations, okay? So that way, eigenvalues and eigenvectors and spectral theorem may come to be handy for this problem. And if, for whatever reason, this problem comes to be nonlinear, I'm going to discuss what that means, we can still linearize it and use eigenvalues and eigenvectors. All right? Because locally, everything can look, you can make everything to look linear. I will say shortly what is a linear and a nonlinear ODE. So the order of a differential equation, can you guess from these equations, these examples, what do I call an order of a differential equation? What defines the order? It's the highest derivative, basically, that you have, right? So this is a first order. This is a second order. We're going to spend at least 3 lectures to discuss these equations because they are essential for vibration models and also in electrical engineering. So second order ODEs. This is a fourth order equation. This is sort of the Laplace equation here. You know, a second order involves second order partial derivatives. So here is the general form of an nth order ordinary differential equation. Usually what we do is we try and we hope that in most cases we can separate the nth derivative and put everything else on the right-hand side as some function of explicitly of time and all the derivatives up to the n-1 derivative, okay? So we're going to, this is sort of the standard form, so it's possible your equation may not be on that form, but it would be very nice if you somehow can bring the equation to this form. So looking at this equation, can you tell me this general ordinary differential equation, when should we call it a linear equation? I mean, what will be a natural definition of a linear ordinary differential equation? So what type of functions you would like to have here, right? Because that, it's everything that is hidden if this is linear or nonlinear. What type of function do you expect to have? Polynomial, you said? So you would like to have combination of all of these derivatives, but the coefficients in the combinations cannot be functions. So for example, the coefficient on y cannot be function of y prime, y double prime, etc. It has to be a function of time only, or constant. Okay? So if it is, in the general case, if the coefficients, this combination of these derivatives are functions of time, this equation is still a linear equation. But if the combination, let's say, if you have a term that involves y times y prime or y squared times y double prime, that's a nonlinear differential equation. And that's bad news. Okay? So for example, can you tell me what equation is this, the last one? Is it, I mean, it's a partial differential equation, but is it linear or nonlinear? Nonlinear, you notice the coefficient is the sign of the depending variable u, right? So here you have a coefficient that is a function of u. How about this equation here? Linear or nonlinear? Say it again. I didn't like what I heard, so don't say it. What is this equation? Linear, because the coefficients are only functions of time, okay? And for example, you can see equation 2, you have e to y times y prime, so that's a nonlinear equation. By the way, I'm going to say something about linear and nonlinear equations in one lecture, because I will need to tell you how to linearize equations and discuss about stability of solutions with the linearized equations. All right, so we're interested obviously to solve equations, so we are looking for a function phi of t that when we can plug it in this equation, it satisfies this equation on some interval, right? I mean, you don't want to find a solution that's only valid at one point. That is not going to be very helpful. So you need to have at least some open interval where there is a function phi that satisfies this. And if you take this simple equation, if you plug in sines or cosines, right, and I give you different options here, all of them are solutions of this equation, which actually implies, by looking at the last equation, that when you haven't brought in initial conditions yet, there's a whole class of solutions. You don't have a, so they, here, for example, both sine of t is a solution, and minus cosine of t is a solution. So which one actually will be useful for your problem depends what initial conditions you start, and that will define which of these solutions you should actually keep. So we will need to compute the very general solution without reference to initial conditions, and then we will need to actually plug in the initial conditions. And I will be more interested actually in our lectures not to bother too much with initial conditions, because I want you to understand what the equation tells you regardless of where you start, all right? If you start here, will it be, eventually will be a stable solution, or, are you going to grow exponentially? So we want to see a whole class of solutions implied by the differential equation. So obviously, this is not the right course to do these things. I haven't said anything, right? I mean, if I give you an equation, somebody will say, do you really have a solution to that equation? Okay? And if you take a rigorous course, you will learn under which conditions, not just ordinary differential equations, but PDEs have a solution. This is what goes with the name existence of solution. If there is a solution, you may be asking, is this the only solution? Do I have a unique solution? There are some very interesting equations in physics that have multiple solutions. Okay? In dynamical systems, you all know, right? You start with something, and somehow something goes crazy, and suddenly you see yourself jumping up there, okay? Because the system is unstable, giving you multiple solutions. So this issue of uniqueness, it's extremely important. Again, we are not going to do any proofs in this course because we are elementary in whatever we cover. Somebody asked if we're going to do numerics. I will mention a few things. Actually, if I have time, even in the lecture today, I'm going to tell you about the Euler method. But really, this is not a course about solving numerically ODEs or PDEs. Okay? So most of the discussion will be on analytical solutions. And we're going to use computers to be able to assist us in visualizing the solutions without having to spend days doing calculations by hand. Okay? But I am not going to ask you to write computer programs to approximate the solution for this on your own, right? MATLAB and Mathematica will do this for you. Okay, So let me do, so these are the two problems. You remember we had this falling ball under gravity and some air resistance, and then we had this population of mice given by this equation. So we want to solve these problems. They fit under this category, y prime equal a y minus b. So I'm going to go rapidly to discuss this. The solution of these equations, actually, you don't need to learn anything from me. It's basic trivial manipulations of calculus. So for example, this equation here is dp over dt, right? dp over dt. So you can rewrite the whole equation as dp divided by p minus 900 equal to 0.5 times dt. And then directly you can integrate that. Everybody can see that? I mean, I can do this because I only have one dependent variable and one independent variable. So everything is legal here, all right? So I can take dp over dt equal to that, and I can write dp over this equal to 0.5 dt. You see that? Yes? All right? And then means on the left-hand side, it's only a function of p. On the right-hand side is only a function of t, so I can integrate. So an equation that I can do this is called what? There is a name to it. How do we call equations where you can separate variables and integrate independently? Separable, thank you. So if you do the integration, okay, you get a log from here, etc. And here is the solution, okay? So the solution basically looks 900. And you remember what was that 900? Wasn't it that the equilibrium solution? You remember? Okay. So we get the equilibrium solution plus some constant times e to the 0.5 times 0.5 t. Okay. So obviously, depending on that constant k, you may have, for example, if k is positive, as t goes to infinity, this will go to infinity. If k is negative, you will go to minus infinity. Okay. And for t equal to 0, you had that equilibrium p equal to 900. Okay. So this is sort of a plot of a family of solutions for different k's. So you should learn how to do this with MATLAB on the same plot. If you have a constants of integration, you should be able to take this and put different constants and actually show the solutions on a given interval. Okay? So all of them start with the same initial, they start basically in this neighborhood, okay? And I'm using different k's to compute different solutions from this family of solutions. And again, here is now the solution with this direction field, okay? To see why it is important to have an idea of how the direction field looks like, okay? So what can you say here? That if you start with initial population below 900, you remember what, you follow the arrows basically, and the arrows take you where? This is the population problem, so eventually you will go, so what happens if, so let's look at this equation. Where is it? All right? Can you describe me with words how do I get this solution that goes down? What k comes in that picture? If you have a population, let's say 850, is k going to come at time 0? Is k going to come positive or negative? So if you have a population below the equilibrium 900, okay, so at time 0, if the total population is 880, is k going to come to be positive or negative? Negative. So if it's coming negative, the solution is going to be 900 plus minus something negative, right? E to the 0.5 t, and that gives you the decay, all right? So it decays exponentially, and the population will go to distinction. And that's what you see here. The idea of the arrows, you don't really have to solve the equation. If you have these arrows, you start from the initial condition, and you follow the directions of the arrows, right? It tells you at each location where to go next. It tells you what the velocity is, right? And so you follow the arrows, and the arrows go downwards, right? That's why you see this path. If you're above 900, you follow the arrows and the arrows go up, the population will grow exponentially. By the way, this little library, this little command in MATLAB that allows you to plot these fields, you can search it and find it. I was thinking of giving you literally a whole program to do this for each problem, but I want you to spend this weekend to actually learn a little bit about ODEs and MATLAB. So how about if you find it, all right? Because you don't want everything ready on the plate to eat, okay? So you can, there's no way you can miss it. If you say direction field ODEs MATLAB, you will come up with about 1,000 references, okay? And you can use any of them. All right. So the initial conditions, this is the problem I mentioned. It will define for what k is. So if you put the at time t, the population to be 850, k comes to minus 50, and this is the solution that we have. And this is, you can see now, the particular solution, all right? The idea here is the direction field is way more important information than one solution, right? I mean, if you plot me this solution, fine, but it doesn't tell me the whole class of solutions that I may be interested depending on different initial conditions. But this direction field tells me anything. If I start with 1100 population at time 0, it tells me it will grow exponentially, all right? It tells me that there is an equilibrium state. If you only plot for me this blue line, what does that help me? You're solving one problem. I want to solve a whole class of problems. All right, and if you want to solve the general equation, right, this is the same problem with just general parameters A and B. You do separation of variables again, and the solution looks exactly as what we had before, so I'm not going to repeat it, okay? This is the equilibrium solution B over A, okay, plus k times c to the AT. And if you have an initial condition, you can plug it in. And here is the solution with some initial condition y0. Okay? By the way, the ODE toolbox from MATLAB, obviously, in the same program, you'll be able to solve the ODE for any initial conditions. It's one command, one line. You have to prescribe the ODE, right? And the initial conditions, the interval, you want to plot it, and it does everything for you in one line. Okay? So it's nothing to panic. Okay, and again, you can see from the general solution, right? So if this is the general solution, the type of solutions you get, they depend on two factors, right? So they depend on the exponent there. And this exponent is this coefficient A. So can you see immediately that if you have e to a positive number time, right, this will grow exponentially. And will grow exponentially to plus infinity if this coefficient is positive, or it will decrease exponentially to minus infinity if this coefficient is negative. So there is two parameters that you need to worry when you discuss about the solutions and the nature of the solutions is this coefficient A, do you have a growth or decay, is it positive or negative? And then this y0 minus BA. So depending if you start above or below the equilibrium state, that will tell you if you're going to go to infinity or minus infinity. Okay? So nothing, again, all of these equations that you see written here, right, depending on all these combinations, you can actually look at this, where was it? You can look at this picture and you say, yeah, it's all there. I don't have to write all these equations, okay, because it's all there. Okay, the solutions I gave you for the homework, this velocity field, right, this direction field, looks way more interesting than this simple problem, okay? So enjoy. Okay, so this is, again, I'm not going to do this example. This is the falling ball. So I put some initial condition. So if the initial velocity, if you drop it with 0 velocity, and you want to find the velocity at all times, this is how the velocity looks like. Okay, and you did this in your dynamics class, or somebody can say, if I drop it from this height, can you tell me what is the velocity when it reaches the ground. And so, you can put v to be ds over dt and solve also for the displacement. But right now, I'm just showing you the direction field only using the velocity and a particular solution where you start with a zero initial velocity at time 0. And you can see you are approaching here. You're approaching the equilibrium solution. Okay? You can see as t goes to infinity, what happens to this solution? As t goes to infinity, where do you go? Right? Where are you going? To 49. And where is 49, comes? You know what the 49 is? Is 9.8 divided by 0.2. Right? It's an equilibrium place to be because v prime there is equal to 0. All right, I'm not going to do this thing with the displacements. You can actually read this. Okay? So I already said all of these things, so I keep going, right? Because don't want to bore you on this lecture. So as I mentioned, if I give you an ODE that looks not in the standard form that you see here, all right? So if I give you something that looks like this, try to always put it on the standard form like this. So you have y prime equal to some function of x and y or some function of time and y, okay? So this is the standard form that we would like to use in our calculations. Okay, so we discuss about this. We discuss about solutions of ODEs, right? I mean, if you take this, what's the solution of y prime equal to cosine of x? I mean, you can integrate and tell me directly what's the integral of cosine of x? Sine of x plus constant, right? So if you go and plug in different constants of integration, you get all of this. All of these are solutions of the ODE, and I'm plotting this for different constants. Actually, again, MATLAB allows you to plot the multiple solutions of an ODE for different constants or initial conditions. But here you can see that this ODE has a whole class that is sine plus some constant. I actually have discussed about this. You know what? If I can only find it, okay. So we talked about the initial value problem, all right? So initial value problem, again, as we have used t here explicitly, you have y prime equals some function of t and y, and then you prescribe the solution at the initial time. That's what we call an initial value problem. If I can only go, okay, I keep clicking. I hate this clicking because I want to go directly so I can teach you at least one of the methods. All right. Well, it's not yet here. Okay. How do you like this direction field? So you don't see what the equation is, right? So I don't tell you what the equation is, but let me say that I have some equation, and the direction field looks like that. And you see three particular solutions. Can you tell me the nature of solutions that you observe looking at this direction field for this differential equation that you don't know what it is? Tell me what's going on. What do you think happens below this line? Huh? I don't hear you. So if I start anywhere in this region, where am I going to find myself as t goes to infinity? Obviously, I'm going to be going somewhere down there, right? I will never be able to cross this line, okay? So I'm going to go to minus infinity. Now, what happens if I start somewhere in this region, above this straight line? So eventually the solution goes to infinity, positive infinity. Okay? And so let me see, what is the simple differential equation is y prime equal y plus x, or y plus t. Okay? So, and again, how did I calculate this direction field? You know, I took basically the right-hand side, and I evaluated for different x's and y's, okay? And I plotted y prime, all right, with these little arrows. And effectively, you know what you plot? You plot what is called isoclines. You know the word iso in Greek? What does it mean, isocline? Effectively, you plot contours that have what? The same, iso means the same, and cline means what? Isocline, the same slope, okay? So effectively, we plot contours of the same slope, and that's what actually MATLAB does for you, okay? It plots contours that have the same slope, and it does it, you know, with a discretization, not in a continuous fashion, and it gives you these little arrows that define what the solution of this ODE looks like. Okay. All right. So let me mention not that we will do numerical methods, right? But you may wonder, when you ask MATLAB to actually compute for you the solution of an ODE, so MATLAB is not actually going to do symbolic integration of the ODE to tell you what the solution is. I mean, Mathematica can do that. Most probably MATLAB can do it, but the programs you will use with MATLAB will actually do numerical integration to solve the ODE. And so I wanted to tell you, because you're going to use this even in your first homework, what does it mean to do numerical integration? Think of x again being time here with some initial condition. What does it mean, numerical integration? And the most famous method to do numerical integration for ODEs is what's called the Euler method. Anybody knows what the Euler method is? 5 bonus points. You do? All right, I'm listening. Yeah, give me the first order approximation. Minus 3 bonus points. Exactly. So for example, if you start with an initial solution at time x0, time 0, right, that is y0, at the next time step that I call here delta t equal to h, all right, that's my next time step, h, that's my incremental time step. The solution y1 is y0, where you started, plus h times the approximation of the derivative, where the derivative is approximated at the initial state x0 and y0. This is what's called the Euler method, okay? And if you want to see this graphically, here it is, okay? If you are at x0 and y0, okay, and you want to move to a new location x1 or time t1 on a time interval h, what you do is this new solution, you approximate as y0 plus h times the slope computed at x0, y0, and the slope is f of x0, y0. So you approximate the solution there, even though the actual solution is up there. All right, so this is a very crude approximation, but Euler method is sort of the mother of all numerical methods for integrating ODEs. So whatever you do at the end of the day, you're going to be doing some comparison with the Euler method. And so MATLAB most probably will use something else as a default method that is a higher accuracy method. But the Euler method is the standard method for comparison and referring to in all cases. So again, the equation that you will, the MATLAB program will be using to give you solutions starting with some initial conditions will be some sort of approximations that look like that. You start from where you are, and then you do one step. And this step here is what we call an explicit step. Because to do this step, you don't really need to know the slope at x1, y1, because this is what you need to compute. you use basically the slope computed at x0 and y0 at the beginning of the step where you know things. It's an explicit method, okay? And of course, if you are interested, you can learn more about Runge-Kutta methods and Crank-Nicholson and all of these other nice methods for doing ODEs. Okay. I think, okay, so we discussed about separable ODEs, so this is the general case. I don't want to do it, okay, come on. This is another example of separable ODEs. All right, so let me do an example. Again, it's 11:20. Most probably I will need to start this again on Monday on using this concept of what is called integrating factors to solve ODEs, okay? So let me go directly to the problem. Suppose you want to solve the equation that looks like y prime plus 1/2 y equal e to the t over 3. Okay, so my independent variable is t. So what we would like is we would like to make this equation a separable equation, right? Having on the left-hand side only y, on the right-hand side having only time, so we can integrate. So here is the trick that you do. You are multiplying this equation with some unknown function that I call mu of t. Not known what it is. You will see why this method is called the integrating factor. I multiply this with some unknown mu of t. And then this equation takes this form. Nothing new, okay? Now, remember if you take the derivative of the product of two functions, how does the derivative look? If I take the derivative of u times v, how does the derivative look? uv prime plus v prime u, all right? So can you make actually the left-hand side as mu times dy dt plus the derivative of mu times y? Can you make this as the differential actually of the product of two functions? And to be able to do that, the derivative of mu has to be equal to what? Say it again. Mu over 2, right? So if you take mu prime to be mu over 2, all right, so if you do this assumption, then effectively, all right, this is what I'm going to use, okay? All right, so we're going to choose mu prime to be mu over 2, which means mu is going to be e to the t over 2. And let me just finish before my clock hits me there. If you take mu equal e to t over 2, then this, when we had multiplied by mu, and I put mu explicitly here, the left-hand side becomes the derivative of e to the t over 2 times y equal to that. And that's a separable equation, right? Only y there and only t there, so I can solve it, and there's the solution. So this concept of being able to identify an integrating factor, okay, that separates the equation, it's a very nice trick for ordinary differential equations. And actually, you can generalize to other methods as well, so we will use it as we move along in the course. 11:23 done, so have a good weekend, and I'll see you on Monday, okay? And the homework is a little bit lengthy, or it looks lengthy, so please start it early.